Hey. Hi. Um, this is another one of those topics I'm a little wishy-washy about. Like, really? Okay. So we're gonna do it. Topic 7.7. There's a hair on me. And it's called representations of equilibrium. This will be short. Imagine. Should be. Cross your fingers that all goes well. Let's share a screen and share. I'm referencing the notes and the PowerPoint. I'm going to start. Oh, I gotta share my screen. Oh, I hate it when that happens. Screen mirroring, blah, blah, blah. Come on, come on, come on. Just found out I'm going back to school on January 4th. I really do like working from home. Okay. All right. I know it's best for y'all to go back, but I didn't know if y'all are gonna go back. What do we have? Representations of equilibrium. To be honest with you, I'm gonna go straight. I am gonna go straight to the notes. All right. I am on page 6 of your unit 7 notes, task 7.2. Not much to talk about. He calls it 7.2. AP calls it 7.6 or something, or 8. I don't know why the difference. In the diagram to the right that represents an equilibrium at a certain temperature for the reaction, where pink is H, green is I, and pink and green is HI. All right. What can be said about the equilibrium position in terms of reactants and products, the likely magnitude of K, and the extent to which the reaction proceeds? Well, all we're going to do, guys, is you should have learned by now with these particular diagrams to start counting. HI, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. We've got 14 of these at equilibrium. 1, 2 of these, and 1, 2 of these. Well, that tells us a lot. What can be said about the equilibrium position? Let's just look at what words would we say? We would say the equilibrium position. You could say lies to the right, or is with the reactants. You could say that this is reactant. Oh gosh, products, sorry. I'm so glad I caught that. Is with the products over to the right, right? Because we got lots of products and a little bit of reactants. We could say that this is not reactant, rather, this is product favored, right? Those are some words. The equilibrium position lies to the right. I mean, that's what you say. That's just kind of how that goes. In terms of reactants or products, right? So equilibrium lies to the right. It is with the products. I could say it is with the products. It lies to the right is with the products, as there are many more products present than reactants, right? I told you I was kind of like, why are they asking us to do this? I guess to make sure you can look at a visual. The likely magnitude of K, what's going to be the magnitude of K? K is going to be very large. Right? Essentially, it's 14 squared divided by 4. And the extent to which the reaction proceeds. Reaction proceeds to a great extent, right? These are not FRQs. Reaction proceeds to a great extent, and we know that because of the value of K. All right. Let's look at what we have available to us in our PowerPoint. And there's not much. There's what you need to know. Your objective: represent a system undergoing a reversible reaction with a particulate model. Particulate representation can be used to describe the relative numbers of reactants or products prior to and at equilibrium. Okay. Okay. Sorry, I'm just kind of looking there. What I notice here in this first graph, these are my concentrations. So at this point, the substance is at equilibrium. And then what we see is that right here, something happened. Something happened to disturb, right? Equilibrium was disturbed. Let's look at what happened. It looks like we had an increase of nitrogen. So it looks like the concentration of nitrogen must have gone up, right? Which, what would that do? That would cause the rate of the forward to do what? It would now be greater than the rate of the reverse. We talked about this because we would have more reactants to collide, so we'd have a greater likelihood of successful collision, so we'd have a greater rate, and we would need to reestablish equilibrium because we just messed it up, right? So notice that what happens, what we need we're going to make more products, right, at the expense of our reactants. Let's see if that's what happens in our graph. Let's see. Well, H2 was a reactant. H2 went down. And in H3, maybe I analyzed that incorrectly. Imagine I'm doing N2 plus H3. Let's see. So if hydrogen went down and nitrogen went up and ammonia went down, oh, then we must have removed the hydrogen. That's what we did, which is still what we see here. We removed a reactant. So the rate of the forward would actually be less than the rate of the reverse. Whoops, might need to redo this one. Would actually be less. So those had to make sense. So I hope you can learn how you have to work your way through this. We must have removed some reactants such that we needed to make some more so that that forward reaction could speed up. So we should see more of this. And in fact, that's what's happening with our H plus, and the ammonium is going down. So my original thought, it didn't work. And I knew when I saw that my ammonium had decreased, because based on my logic, it would have increased. So I had to fix my logic, okay? And I think that's okay. And I'll have charts like this for you to look at, all right? I don't know what's going on here, and I don't really want, it doesn't make any sense to me. Original equilibrium, let's see. PCl3, PCl5, so 1, 2, I don't know what we're supposed to be noticing here, 3, so we have 3 of these, we have 1, 2, 3 of these, and we have 1, 2, 3 of these. Immediately after volume change, okay, so the volume was cut in half, volume decreased. Where's the new equilibrium? I don't see anything there, but I would imagine I would need to see a chemical equation. I'm a little confused of what I'm supposed to do here. If you have an idea, I would in the pre-sheet. Oh, I think I'm supposed to, Okay. Let's go like this. I think this one kind of jumped ahead of us, to be honest with you. Notice this is balanced 1 to 1 to 1. This is ahead of us, but the volume decreased. Therefore, the pressure increased. The system's going to do what it can to reestablish equilibrium. It will need to shift to decrease the pressure. So that would be shifting towards the product side where there are less moles of gas. So what I should see over here in terms of drawing is more PCl5s, right? And less PCl3s and Cl2s. So maybe I will add this, I will make this 5 and make this 1 and make this 1. So we're actually supposed to draw those particles in there, right? So like I said, we'll, right, watch your stoichiometry. He'll gain 2, right? So he'll lose 2 and he'll lose 2. So that would give us a total of 1 PCl3, 1 Cl2, and 5 PCl5s. No one is grading you on your drawing, okay? And if you're going to say 1, 2, 3, 4, Miss Murphy, could I just write those in there? Probably, right? Anyone who counted that wrong, unless the directions particularly told you not to. They just, it's this, you're being graded on the chemistry. That's good chemistry. Okay. Let us leave it at that. You may not have understood this right here. I don't that shouldn't be here. This question shouldn't be here, but it had particular drawings. So I'm going to stop now, and I'm going to come back with the next video. So you'll see me wearing my gloves, same clothes, everything.